Section 6.5, Assessing Normality. At the end of the textbook on Appendix B, there are so many data sets. Each data set are for like body data, food and height, body temperatures, birth, family height, freshman 15. So you see that there are so many numbers here. Now, if I plot all these numbers, then I can tell whether distribution is normal or not. But sometimes there are so many numbers to input into the calculator or the computer. Like in this case, there are, so bare measurement, there are all these numbers. So in that case, what we do in this section is to see if the final graph is a normal distribution, which is the bell shape or not. Instead of typing all the numbers, we just randomly select some. We randomly select some of the numbers, and based on those numbers, when we plot, we could tell whether the function is normally distributed or not. For instance, if the histogram is kind of symmetric, increase and then lower, then you have normal distributions. Or if the histogram looks like this, that means it's not a normal distribution. You see the tails is to the right. So for that, there is a procedure that we follow these procedures, and we tell whether it is the normal, uniform, or skew. In case of normal, when we have a graph, then you see all the points that all these data points are clustered around the straight line. So that means it's normally distributed, or in this picture, it's like uniform. But when we point those numbers, if they're scattered and you cannot really draw a straight line through all of them and numbers are not close to that, then you could claim that original shape is not normally distributed. So you could tell here, these are some examples. And like number 5, these pictures, the answer is no. When you plot all the points, this is what you see. It's kind of curved, it's not on the straight line. Or number 6, all the points are kind of adjacent to a straight line. So you could basically through a line through this straight line, and numbers are clustered to this number line. So the answer is yes. You could claim based on these samples that original function is normally distributed. Number 7 is yes. So number 5, no. This one, yes, yes, and no. They call it quantile plot. These are quantile plots. So interpreting normal quantile plot would tell us whether the original function is normally distributed or not. Like what we do here, at the end of the book, we have data set 23. Data set 23 has 250 numbers. Out of these 250 numbers, all we do is just select 5 numbers, randomly select 5 numbers, and we do our study. We do our study only on 5 numbers versus 250 numbers. So we randomly select those numbers, select 5 numbers out of 250, then we are using this formula, 1 over 2n, 3 over 2n, 5 over 2n. What is the value of n? 1, 2, 3, 4. We selecting 5 numbers. So when you put 5 here, then would be 1 over 10, 3 over 10, 5 over 10, 7. So we can come up with these numbers. These are the area. So when you selecting 5 numbers, n is 5. Then you come up with all these numbers. You put those numbers on the tables. Now, each of these is the area. What's the z value when the area is 0.1? Like here, if your area is, if this area is 0.1, what is the z value? You could use the calculator. Second verse, inverse norm, 0.1. Calculator would give you the number, minus 1.28. You could also calculate for 0.3, 0.5, 0.7, 0.9. Now, then you have a new table. This table, x value are these numbers that we select in the problems. These are your x values. What are the y value? The y value are these, the z value. Then you go ahead and plot all these points. When you plot all these points, you see something like this. The point do not lie on a straight line. So we conclude that 5 numbers are not coming from the normally distributed. So original data are not normally distributed. This is how, so when you draw a straight line, you see all the numbers are not normally distributed. This is another example, again from data set number 9. We collect 5 numbers. So this is 10. Now, if you want to use your calculator to graph, this is how to do it. So you put these numbers on L1. These are L1. These are L2. And then that will give you all the points. Then you see whether they are on a straight line or not. In these examples, there are 1, 2, 3, 4, 5, 6, 7, 8 numbers. So n is 8. In that case, all the values are 116, 316, and so on. So based on those, you find your z value, then you put the z value here. And you see the points are like this, not a normal distributed. So that's the way to do it. You graph it, you plot it, and then I put the answer for each of this problem here. So, and the key is here. So you could tell from the graph whether function is normally distributed or not. Look, see, it's not normally distributed because you see it's kind of curved and it's not adjacent to the straight line. So the key for all of these are listed here. On this one, there are 1, 2, 3, 4, 5, 6, 7, 8 numbers again. So based on these 8 numbers, first you find your z value. Z value based on all of this. 1 over 16. See, I show you for one example here. You go to second verse, inverse norm. For inverse norm, You could just put the fractions. For example, you want to find it for 316 to see what the z-value for 316, just put 3/16 on the second verse. When you find a z-value, then x are the original numbers in the problems, and z are these numbers. You graph it. Now you see all the points are not on the straight line. And you could use your calculator to actually see that. The stat plot, select the last graph, and zoom step. And that's the instruction to do it. Again, number 7, number 8, and 9, they all are multiple choice, and the keys are here.